Welcome to day 3 of the 60-day Rust DSA challenge. Yesterday, we covered ownership and borrowing. Today, we are getting into the two containers you will use for practically every algorithm you write in Rust: fixed-size arrays and vec. These seem simple, but there are details here that directly affect whether your code panics, allocates unnecessarily, or runs efficiently. Let us get into it. First, fixed-size arrays. When you write let arr colon bracket I32 semicolon 5 bracket equals bracket 1 comma 2 comma 3 comma 4 comma 5 bracket, that array lives entirely on the stack. No heap allocation, no pointer indirection, no capacity tracking. The size is literally part of the type. An array of 5 I32s and an array of 6 I32s are different types. You cannot pass one where the other is expected. This is strict, but it means the compiler knows exactly how much memory to reserve. For small fixed buffers inside algorithms, like a 26-element character frequency counter, arrays are perfect. Zero overhead, cache-friendly, and the compiler can sometimes even keep them in registers. Now vec. Vec of t is Rust's growable array. Under the hood, it is 3 values on the stack: a pointer to heap allocated memory, the current length, and the current capacity. When you push an element and length equals capacity, vec allocates a new buffer, typically double the old size, copies everything over, and frees the old buffer. This doubling strategy gives you amortized O of one push. If you push in elements, you will trigger roughly log base 2 of n reallocations, and the total number of element copies across all those reallocations adds up to about 2n. So per element, the average cost is constant. But those individual reallocations can be expensive, especially for large vecs. That is why vec with underscore capacity exists. If you know you are going to push exactly n elements, call vec with underscore capacity n. 1 allocation, 0 reallocations, 0 copies. In DSA code, you almost always know the output size. Building a prefix sum array, same length as input. Filtering elements, at most the input length. Merging 2 sorted arrays, some of their lengths. Get in the habit of using with underscore capacity. Here is a concrete example. Say you are computing a running sum. You take a slice of I32s, create a result vec with underscore capacity nums.len, then loop through accumulating the sum and pushing each value. 1 allocation for the exact size needed. Now the gotcha that catches everyone at least once. Vec bang bracket 0 semicolon in bracket creates a vec with length n, filled with zeros. You can immediately index into position 3 because there are n elements in there. But vec with underscore capacity n creates a vec with length 0. The capacity is n, meaning it has reserved space, but there are no elements yet. If you try to index into position 3, you get a panic. This distinction matters a lot for DSA. Use vec bang bracket 0 semicolon in bracket for DP tables, visited arrays, distance arrays, anywhere you need pre-initialized storage. Use with underscore capacity when you plan to populate the vec by pushing. Let us talk about slices. A slice, written as ampersand bracket t bracket, is a fat pointer. It stores a pointer and a length. Slices are how you pass array data to functions without caring whether the caller has an array or a vec. When you write a function that takes ampersand bracket I32 bracket, it works with both. This is idiomatic Rust. Never write a function that takes ampersand vec of I32 unless you specifically need vec methods like push. Slice syntax using ranges gives you zero-cost views into data. Nums bracket I.j bracket is elements from index I to j minus 1. Nums bracket .k bracket is the first k elements. Nums bracket k bracket is everything from k onward. These do not copy data. They just adjust the pointer and length. For divide and conquer algorithms where you split an array in half, this is exactly what you want. A few slice and vec methods that come up in almost every DSA problem. Sort underscore unstable sorts in place and is faster than sort because it does not. Guarantees stable ordering of equal elements. For algorithm problems, use sort underscore unstable by default. Binary underscore search returns a result. OK with the index if found, or error with the insertion point if not found. That error variant is incredibly useful for problems involving sorted data. Windows of n gives an iterator over overlapping subslices of size n, perfect for sliding window problems. And swap takes two indices and swaps the elements in place, which you need for partition-based algorithms and certain sorting implementations. Quick recap. Arrays are stack allocated, fixed size, zero overhead. Vec is heap allocated, growable, with amortized O of 1 push. Use with underscore capacity when you know the size. Use vec bang with a default value for pre-filled storage. Accept slices and function signatures. Use sort underscore unstable over sort. Tomorrow, day 4, we implement linear search with proper generics and trait bounds. See you then.